So let's start, guys. Did we cover shortest path? Seems like we did because people are talking. You already know it. Did we do? But we actually covered it a bit. Did we? Shortest path. You didn't. We didn't cover it. In the depth first search? Exactly. So in the BFS, we said you can actually get the shortest path, but there was a problem with the BFS.
The distances are the same. We're assuming that.
Exactly. When the edges are all equal to the same weight, for example, I always have every edge equal to 1. That's when you use the BFS, is going to work. But in real life, lots of applications, that's not the case. Why? So let's take a look at this one. So if this is an airport, and the edges represents what? The distance between cities. Can they have the same distance? So in this case, I cannot use BFS. I have to use something else. So for example, here, I want to check what is the shortest path starting from Providence to Honolulu. So I can't use BFS. I have to use another algorithm. We're going to learn it. Okay, why? Because as you can see here, these are different weights. For example, here they can represent distance, but sometimes they will represent driving the directions. So what do we mean by that? Let's take the Google Maps again example here. So what would the edges weight be in the Google Maps? Who can tell me? Edges are what in Google Maps? Streets. Back then, in the BFS, we reduced to as if like every single street is 1 kilometer. I gave you the answer. Partially. But here, we're going to say these edges in Google Map will represent what? The shortest, when you open Google Maps, what does it tell you? The shortest what? Route, for example. So they can represent distance, but what can you play around in Google Maps? When you go to the shortest time, what are the edges represented now? Time, not distance. You see, guys, why these are important? So the edges can represent, depends on you, on your application. And Google Maps, it gives you the option. Shortest distance you want. Why? Maybe you don't have enough fuel. You want to go to the shortest distance, even if it's longer time. Or you're late and you want to go with the shortest time. Okay, so these, the shortest time or short distance, these kind of like the edges. So it depends on this. It will help you to go from place to place. Again, also what we can do is that if I tell you, you can actually find again the tree of the shortest path. So this tree here, when you're doing the spanning tree, is going to have the shortest path tree, because sometimes, like using the DFS, for example, you can have a spanning tree, but it's not going to be the shortest path. But in this case here, no, it's going to be the shortest path, like with a tree, which is, tree is what? Without cycles. Okay, so let's skip these things. Now, very important thing, because we're going to learn something else other than Dijkstra. The way we're going to think, as usual, what is the problem and which algorithm I'm going to use. Now, if you have a problem that you want to, all the weights of the edges are the same, you're going to tell me, you know, BFS is enough. That's the algorithm that I'm going to choose. Now, the problem that, no, they are not the same weights. So you're going to use Dijkstra. But also, one of the part of the problem that the graph has to be connected for Dijkstra to work. You remember when we said sometimes the graph can be like this? This will not work with Dijkstra. No, you'll be able to visit this. You're going to stop. That means you're not going to be able to do the shortest path. Exactly. So it's going to be only on this component. Right? So, and then also the edge weights need to be non-negative. They can't be negative. In this case, you can use Dijkstra. Now someone's, how would the edges be negative? How can a distance on time or time be negative? Who's thinking like this? But, so my answer for this would be what? That's not the only application on Earth, right? Where we're only using Dijkstra or like using something for what distance and time. What if we're using the graph? Do you remember when we said 50% of the application can be solved by graph? What if we're using graph for financial application? If you're on debt, if you have debt, you're going to have minus and the money, for example, okay? Credit versus debit, all of these kind of things. Now, for some reason, for mathematical reasons, stuff's not going to work with Dijkstra for non-negative. In this case, when you don't have a connected graph or you have a negative, that's where we're going to go and choose another algorithm that we're going to learn about later. So for now, these are very important. Also, the graph may be directed or undirected. It's not going to matter for Dijkstra. It's going to work for both. Okay, so what is Dijkstra? We're going to build a cloud starting from the node that we want to start from. So if I'm telling you I want to do the shortest path starting from A, so that means the first thing that you want to do is you're going to build a cloud next to A, and then this cloud is going to expand. Now, how is it going to expand? In the first thing, these are what the weights of the edges. So I have here 8, 2, 4, whatever, all these are the weight. The first thing that we're going to do in Dijkstra, all the adjacent nodes connected to from where you want to start, we're going to update their weights. So what is the updated weight of B? In the beginning, 0 plus 8. So I'm starting from 0, and the road is 8. So this is going to be 8. For C, it's going to be what? 0 plus 2, that's 2. For D, 4. And now any node that's not connected to, it's not adjacent to me, it's going to be infinity. That means any very big number. I'm going to put it like this. So I'm initializing it as infinity. Now, the next step would be what? How can we move from A and visit? DFS, we said we're going to start, for example, per order, that I'm giving you the order, and then you're going to go depth. BFS, you're going to start per order, but it's going to be like a cube. Here, because there is weights, it's not going to be per order. It's going to be per what? It's the shortest path. Per what? Per weight. If you look at this, guys, 8, 2, 4. Which one are we going to visit first? C, correct? So that's C. Now, you arrive at C. So the idea of the Dijkstra, you expand the cloud and you update. So now I arrived at C. What am I going to do? I'm going to look at all the adjacent neighbors and update them with the new weight. If it's better, what do you mean by this? This one here was 8, and this one was 4, correct? So let's look at the 4 one. This one is 4. The new weight will be 2. That's my weight here. And then 1 is the edge's weight. That's 3. Is 3 better than 4? Yes. I'm going to update it to 3. Now, 2 plus 9, 11. Is it better than infinity? Yes. 2 plus 3, 5. Better than infinity. That's 5. 2 plus 7, 9. Is it better than 8? I'm not going to touch it. That means this road here, it's still the better road.
The edges?
No.
You put 4 and 7 in on dotted lines, like that.
Yeah. So now, forget about the dotted lines. It's going to make sense in a bit. Okay. Focus only on the updates and stuff. So this one I'm not going to touch. Now I have 5. I have 11. I have 3. Where should I go next? 3. Why 3 is the smallest? So, okay, so let's go. First, this update thing, it's called relaxing. So how is it done? This is 50. That's the weight of this node. The edge is 10. This one is 75. 50 plus 10, that's 60. Is 60 better than 75? Yes. I'm going to relax the edges. It's called relax. That means first I had this as the shortest path. Then that's why now this is dotted and this is the one that is a line. That means no, now this is the shortest path. I updated. That's called relaxing. So again, we're doing this. So I'm here, 2, and then we went to D. So I'm at D now. What should I do? Whenever I expand the cloud, I update. Okay, what are the adjacent nodes to D? It's F. F was what? 11. Now 3 plus 5, better than 11, so I'm going to update it, correct? So that's 8. Now I have 8, I have 5, I have 8 here. So where should I go? If you notice, I don't have to only go from D, because this is not a queue, this is not a stack. I don't have to follow the order. We're going to see what are we going to use as a data structure. But for now, you're noticing that we're going always with what? With the shortest weight, with the minimum weight. Riley.
We treated F.
We didn't treat F yet, so we updated any adjacent.
But data is also adjacent to D. We ignored it because it's already in our cloud.
Exactly. Very good, guys. So very good, Riley. So here, what's happening? Anything inside the cloud, you don't touch it because you already visited it. Okay, guys, only the outside the cloud. So that means 8, 5, 8. Obviously, I'm going to go where? To 5. So I'm going to expand to 5. When I expand to 5, I need to update any adjacent nodes of E, the one that I visited, which is outside of the cloud. In this case, which one? It's B. B was 8. I have 5 plus 2. Is it better than 8? Yes, so I'm going to update it. That's 7. Now I have 7 and 8. Which one I should visit? B or F? B. Very good. So I visited B, and then at the end I still have F, so I visited F. Very good. Still confusing. We're going to do a woo clap for it, and it's going to work.
You didn't do anything for B because everything was already in.
Yes. There is no adjacent. So let's go to the woo clap. We'll solve this, and then we'll move to the actual algorithm analysis of it. Because it's interesting. Okay, let's start. We don't have lots of time, so we'll try to finish this. Everyone is in? Okay, let's do this together. Which algorithm is more suitable if I want to find the shortest path? Between these two, of course. DFS or BFS? DFS is depth first search. BFS, of course, BFS. Can I calculate the shortest path using breadth first search if the edges have different weights? Time to wake up. What do you guys think? Of course not. If you have a graph and I'm asking you to use Dijkstra algorithm starting from node A, what would be the output? So I'm telling you, I'm giving you node A. What would be the output? What is Dijkstra used for? Of course, the first one, unless I give you A and D or A and C or A and whatever. If I give you two nodes, that means I'm asking you to do what? To what is the shortest path between A and something. If I don't give you Other node, only one node. That means I want the shortest path to this whole city, for example. That's what Google you do when they scan things. They go everywhere. And then when you are using Google, you're going to give them what? Destination and okay, choose the right answers, property of Dijkstra's algorithm. It can be applied on connected graphs only. It can be negative, and then the graph may be directed or undirected. Now, let's do this together, guys. Given this graph, what is the output after applying Dijkstra algorithm starting from A? And I'm telling you before you answer. Who answered before I give them the instruction? So follow the order. Like, so if in this case they are both equal, B and C, go to B. Because you can have two different answers. But we're asking if you want to go to B. Yes. Sorry? I'm giving you because there is two answers here just for the sake of the exam. Usually we give you strict answer. Like when you're writing your algorithm, you don't want to leave it random. You're going to tell them it's either follow order or follow. Okay, guys. So 50-50. Okay, that means please focus. Guys. So I'm at A. Which one I want to choose first? The first one, B. I gave you the answer. You have to go to B. Now you're at B. What is the weight of C? So what is the weight of C here? 2. What is the weight of B? 2. What is the weight of D? Initially, infinity. Initially, infinity. Now you're at B. So what is the next step? You're going to update all the adjacent. So you're going to update C and D. If they are better, is 2 plus 1, which is 3, better than 2? Okay, so I'm not going to go to C. Is 2 plus 2, that's 4. That's 4. Correct? So I have 4 here and I have 2. Okay, now I finished updating. Which one I should visit, 2 or 4? 2. So I'm going to go from A to C. So this is the one that's going to work. Why? You arrived at B, you don't update C, it's still 2. And then here you update D to 4 because B is 2, this is 2, that's 4. So if you have 4 and you have 2, you're going to go to 2 first. Okay? So okay, we're going to see another example. Let's cover this first. You have this, which one you're going to choose? You want to apply the edge relaxation. So U is 50, Z is 75. Exactly, it's always going to be, of course, this 50 plus 10, 60. That's the rule. Now, let's do this example together. So here, don't look at the dotted edges and colors and stuff, because I did this manually. Just focus on the nodes and the edges, edge numbers, edge weights. So what is the next node to go to? We have B, C, or E. We're warming up. So B, of course. Why B? 2. 2 is better than. We're going to always want to go to the shortest path. Now, after going to the next node, which nodes are going to have updated value? So what is the next node? I'm at B now. So which are the nodes that they are going to have updated values? Again, we're going to use the relaxation method. That means we're only going to update when it's better, correct? In this case, which one are better? Only 50 people answered.
You go for the small.
You have C7, D7, D9, Fn, of course not. So let's take a look. I'm here. 5 plus 2 is what? 7. So that's why we're going to always use 7, not 5. Okay, so it's the weight plus the weight of the edge plus the weight of the node. So C is going to be updated. D is going to be what? 7 plus 2, not 7. In this case, it's going to be 7 and 9. Okay, guys, remember this. You have to remember all of these things. We're going to cover prism and Kruskal and lots of different things where we only use sometimes the edges. So now you can choose more than one option if you want. Which one can be the next node? The new weights are 7, 9. I have 7 here and I have infinity. So is it C, D, or E? I said you can have more than one option. That means you don't have to. C and E, both of them are right answers. Of course, not D, because D is 9, 7. If you want to use the shortest path, you're not going to go to the longest path. Now, after going to the next node, which is what? You're here at C. So you're already here at C. Which ones are going to be updated? So you are at C. First step, what do? I'm going to look at the adjacent nodes to C. What are the adjacent nodes to C? D and E. So F, I'm not going to touch it. D and E. Let's start with D. D is 9. What is the alternative of this? It's 9 plus 7. So of course, I'm not going to update it. Now I look at E. E is 7. What is the alternative? 8 plus 7. I'm not going to update it. Okay? Why it's 8 plus 7? Because the weight of the node is 7. The weight of the edge is 8. I'm always going to add the node weight plus the edge weight. So it is none. Not E and none D. It's none. Who didn't understand this? Please raise your hand so I can explain it so you don't get confused. Yes. Tell me, what did you understand exactly?
I just don't understand.
Which part? I mean, like, why did we choose none? Why it's none? D is what? What is the weight of, guys? What is the weight of D? 9. Correct? No. Now, if I want to update D, it has to be a better weight, like less weight. When we update, we always use this, the edge plus the node. So 9 plus 7. Is it less than 9 or greater than 9? Greater, so I'm not going to update it. Then the same thing for E. The weight is 7. Do I have a better weight? Do I have like less weight? I don't think so. Why? Because 8 plus 7 is greater. So that's the reason why not. Good? Yes.
Update F.
Is it adjacent to C?
When you say adjacent, what do you mean?
Thank you.
Because it's
Adjacent means direct neighbors. So C is direct with what? With D, B, A, E. These are the direct nodes adjacent. Okay? I'm at C. I'm at C, so we are at C. So this one here, you have to imagine that we already have this cloud covering C. But I didn't do it to not give the answer. So it's covering C, so you're at C. Which one are connected to C? D and E. Okay? Good? Any other questions, guys? Ask. It's okay. Yes.
Before that, we said in E. 7.
Yes. And this question here, not we put, you can choose C or E. Yes. No, no, we can't. But in this one, I told you, okay, I choose on your behalf and I chose C. So continue from C. So guys, that's an important question. So when we say here that you have two options, C or E, we don't mean that you can add them both together. Maybe that's why you were confused, right? Because you thought C and E are both inside the cloud, or no, it's different.
No, I was just confused because I thought we could update after.
Okay. Who had yes. Yes, the weight of the node, the one that I'm highlighting in what? In yellow. Okay, so these are the ones that we usually update. So these are already updated from previous question. So here, if you look here, we had it 8 and infinity. So when we updated them, it became 7 and 9. Why 7 and 9? 5 plus 2, 7, 7 plus 2, 9. Good? Ask, guys. Ask. Yes. Sandra. Melanie. It's okay, go ahead.
Okay, nodes that, are, you know, that just visited.
Yes, exactly. Why? Why is this? Because technically,
All the others.
yet, you know what I mean? So you're here, you're going to use what do you know? Sandra. But you don't, so we have A and B in the same cloud, and so you were at A. You added B to the cloud. So you're at B now. So you don't have to go from B. You update all the adjacent connected to B. That's the first step. You're done. Now you can visit any node that is the shortest. That's the minimum place. So that's the idea of the cloud. Yes.
A and B, we can update.
No. You update what. So that's why I'm saying first step, second step. First step, you added B to. So okay, think about it like this, guys. Look, let's say
So when you get
you are here. So that's C. Guys.
sorry, we don't add the adjacent to the cloud. I'm just saying we update the adjacent.
No, but that's what I'm saying. No, you don't. So what you're doing is what? You're A and C. So let's say this is, for example, whatever. You have A here first in the cloud. When you visit C, you're going to do two things. This is the cloud. You're going to add C and update anything connected to C outside the cloud. So B, E, F, D. So that's the step. So that's first step. I added to the cloud. Second step, I update everything. Third step, I can go from anywhere in the cloud. These are the 3 steps. Okay? So guys, 3 steps. Now, maybe you're a bit confused because you're thinking, I'm in the cloud, I was at B, I was at C, how can I add something from B? So let me ask you now a question. Let's forget about this. I think it's clear now how to traverse. But from a data structure perspective, how are we doing this? For example, you're here. So you are here. You just added D, correct? When you added D, you updated F. So that's the second step. So first step, I added D to the cloud. Second step, I updated everything. But then I went from C to E, not from D. In the DFS, we used to have a stack like this. So I couldn't, like, if I'm adding this here, D here, and a stack, I have to pop D, correct? And if I'm doing a queue, and I have D here, I have to also pop D. So which data structure I'm using here? It's definitely not a stack and definitely not a queue. Let's give 1 minute for you to think about it. 1 minute, 60 seconds. Guys, this is a very, very important question. At this point of the course, you need at least to have an idea. Can we use a stack? No. Can we use a queue? No. So what am I following? The shortest path. The shortest path is represented by what? A weight. which weight I'm visiting here? I have 5, I have 8, I have 8. So which weight? The smallest. So priority queue. Why? Because in the priority queue, it doesn't have to be the first one here that I'm going to pop. It's going to always what? DQ, the one with the highest priority. Usually, we call it the minimum key. And then if I'm using this in a heap, I'm taking the root of the tree. You see? Makes sense now how we're using the data structures that we've learned. So we've used stack, queue, and now we're using a priority queue to implement even the graphs and stuff. Right.
So in terms of what we're using this, we're doing like breadth first search and we have a list of all of the edges we do.
Yes.
Here, we're gonna do the same thing, but it's not going to be, it can't be. Because it doesn't,
It's going to be a priority queue.
going to be a priority.
Yeah. The other one, we were using, it's true, we're using a list, but technically we're using a list that acts like a stack, and then a list that acts like a queue. That means in a list, how can a list act like a stack? You say, for example, insert last.
We're not keeping track of the nodes in a priority queue, we're also keeping track of the edges in a priority queue.
Yes, you're going to see how we're going
You're
to
gonna
do it.
get.
You're going, now I'm going to explain. So, but the idea, yes, Veronica.
Is lower, not because the edge of the weight of the.
No, the E. Why E? Because at the end, E already include the edge and other things. Do you see, guys? E already includes everything. Now, this is the total weight. Good? Yeah. Let's go.
It's not a joke anymore.
We use a priority queue to store the vertices not in the cloud. So the one that outside of the cloud, we're going to use for them a priority queue. In each one, we remove from the priority queue. For example, I remove min, I add it to the cloud that can be an array or something. Yes.
So you said priority queue to put in a min heap. When we do the min heap, is that gonna be the short, let's say from the root to any specific?
We're going to see it. I'm going to visualize it for you. Now, it doesn't have to be a heap. It can be also what else we can build? How can we build a priority queue other than a heap? Is it even possible? Did we even learn it in the course? We can have ordered sequence or unordered sequence, correct? So we can have either sequences or a heap to implement the priority. So let's start with a heap first. So before we do the heap, this is an algorithm for this one. Now, this algorithm is not the algorithm. This can be changed. This can be other things can be added to this. For example, here the output is just the label du. You can also have the path with the output. This is just to give you an example. But what are we doing first? So let's look at this. If we want to initialize your v, that's from where you're starting. Correct? I'm starting from v, so I'm going to put it as 0. And we said originally everything else will be what? Infinity, correct? Originally. So in the first beginning thing, I'm going to put everything to infinity, and then I'm going to update them slowly. This will cost me what? The first initialization. Of what? For all the vertices. If I want to update, if I want to initialize, I have this. Okay, so I have 4 vertices. I want to initialize 4 vertices. It's going to take me what? 21? 4. The number of vertices. Okay, so I'm going to loop through the number of vertices to initialize them. It's a normal initialization. So this is going to be n, for example. Now let Q be a priority queue that contains all of the vertices. Now, let's say I'm using a heap and I want to build a queue. So that's the second step. Sorry, I want to build a priority queue using a heap. So I want to build a heap. What is the cost of the heap? The final is in less than a month, or I don't know when. What is the Abed? Or, that's very good. So n log n is one of them, Melanie. And when? So Abed, when would it be n log n?
Well, I know and it's the bottom of the heap construction.
Very good. So n, if I'm using bottom-up heap construction, is going to cost me of n. We're not going to say why. We already covered this. But if I'm using the normal insertion, it's going to be n log n. So here, it's either going to be n log n or n. Depends on how did I build my cube. So let's say n. Then I have this. So this, I'm going to leave it. We're going to cover it. So inside these loops, we're going to have this. So look at this. I'm A. A is, this is the cloud, for example. Okay? No, this is not the cloud. This is the original thing that the graph that you have. I have A. So I'm going to remove A. That's the minimum, of course, because that's the initial one. So let's say I started going to put which one, how they are going to be built, these three, because these are the three that are adjacent to A. Why AC is the root? Why? From a heap perspective, it's the minimum. It has the minimum key. In our case here, what is the minimum key? Is the lowest weight, which is the shortest path. So what do I have here? I have the key, which is the weight, which is 2, but also it includes the path. So which path to C is the one that I'm saying it's 2? Is it BC? Is it DC? Or is AC? It's AC. So I have AC and it's 2. Then I'm going to add the other 2. I don't care about the other 2. So what's going to happen? If I visit C, I'm going to do a remove min, correct? When I remove min here, which one should be on the top? AB or AD?
D.
ADY. It's a minimum heap. So we're going to choose the minimum key. So I'm going to put 4 on the root. This is going to be what? Remove min and update. So I did 4 and 8. So that's the remove min. Then I want to update now. So what's going to happen? This is C. I'm going to update what? D, F, and E. So what's going to happen? How am I going to update them following this, the relaxation update, neighbors, and all of these things? Is 3 better than 4? Yes, I'm going to update it, but then for B, I'm not going to update. These are just the steps that we already explained. So what's going to happen? If you look here, we updated 3, and then we're going to also update E, and then we're going to update F. And we're adding them as a complete binary tree because this is the heap. Now, the next step will be what? Again, I'm going to remove 3, so I'm going to do. So what are we noticing here? When we are removing the minimum, what do we need to do? So in this case here, when I remove this, which one is going to be in its place from a heap perspective? From a heap perspective. 11. So we put this, that's the last one. And then what we do down heap, that means what is the cost of this? That's usually one of the common mistakes that we had in the midterm. When we remove min, what is the cost? O of 1 or O of log n? Why? Because we may have to do the down heap after we remove min. In this case, we put 11, that's O of 1, but then we had to bring 11 down again, so it's going to take me O of log n. So that's one of the things. Now, another thing that's going to cost me is that when I update something, I'm not sure if it shows here, but let's say I'm updating for example, here, CF was 11, correct? But now I'm going to update it with what? With 5 plus 3, with 8. So I updated with 8. In this case, nothing happened. So I updated, nothing happened. But what if I updated and this one here is less than the one above it? Because this is the heap, it has to do what? Up heap. So even the update is going to cost me what at the maximum? Log of n also. So do you see now how this simple algorithm that you're looking at here this one that includes the bigger one, each one can be more than just O of 1. This is not, for example, O of 1. I don't have lots of time. I need to go through this very quickly. Guys, remove min is going to be what? Log of n, correct? We just explained it. Then inside, this, for each vertex now, I'm going to loop. This one is looping through all the n's. That means O of n, this one, the original y. But this one for each vertex z adjacent to u, such that when I'm at C, we said we're only looking at the adjacent. What is the adjacent? Degree of what? Degree of it, right? So we said it, if I'm doing an adjacency list, the adjacent edges are degree of this thing. So this, it's going to cost me the degree of u. And then this one here, we said the change of the key, the update, because of the upheap, it may also cost me O of log n. So this one is inside this for loop. So this times this, it's going to be O of degree u log n. Now, we still have the O of n that's outside. So that's summation from 1 to n. We said the summation of degree of u is what? And undirected. It's going to equal to what? To m. You remember from the slides. That's why these are the boring lecture that we had in the beginning. It's important. We proved that the summation of the degree will reach out to 2 of n. That means O of 2m. That means O of m. Okay? But also I have the log of n here. And I forgot about this log of n. So now these are inside the loop. I'm going to have degree of log of n plus O of log of n. So I don't have lots of time. We're going to go through it, but check it at home. The math will just be like this. Very simple. I'll be 2 plus m, and then it's going to be m log n. Now, the most important thing for me, m log n in the worst case is what? M in the worst case is what? N square. That means in the worst case, I'll end up with what? N square log of n. That's very bad, actually. That's why, guys, what's going to happen when I have a maximum, like a maximum graph, it's not good to do it represented with a heap. We're going to use the ordered, unordered sequence. Why? Because the unordered sequence will take off n square. I know no one is listening anymore, but they are in the slides. Check them, and then I'll see you next day. I'm doing it. Take care.